Okay, thank you all for coming. Good morning. It's my pleasure to welcome Yisong from Caltech to give the talk today. We are academic siblings. We both did our PhD at Cornell under Thorsten Joachims, and he's gone on since then to Disney Research and to Caltech, where he is the director of DOLCET, right, like the Center for Statistical Decision Theory, and he is an assistant professor there. He recently won the Okawa Award. He also gave a very well-attended tutorial on imitation learning a couple of months back. And he is going to tell us a lot more about new frontiers in imitation learning. Thanks, Yisong.
Thank you. It's always a pleasure to be back here at Microsoft Research. I spent one summer at Microsoft Research back in the day. I spent 3 summers total at Microsoft. I fell in love with the summers here in Seattle at the ripe young age of 19. And I couldn't resist keep coming back. I wish I was able to make it for the summertime, maybe some other time. So today I'll be talking about some of the work that about half of my lab has been working on for about the last 4 years in imitation learning. And let me start by talking about some of the motivations for how we even got into this research in the first place. And that is from behavior modeling. As probably many people here are aware, there is a wealth of new tracking technologies that is tracking behavior at unprecedented granularity and volume. So here's a few examples. The first one you see on the top right is the tracking system for the Minnesota Timberwolves Stadium. The Minnesota Timberwolves is a National Basketball Association professional basketball team. And what you see here is a pair of binocular cameras that is tracking the XY coordinates of the players, the game ball, and the referees at 25 hertz. And this technology has been deployed in every NBA stadium. In the middle top, you see an example of me doing a formation analysis in soccer. And this data was collected from the English Premier League in the UK, which is the top professional soccer league in the UK. And again, the tracking system is of a similar flavor as for basketball. And this type of system is deployed in every professional league in the UK. In the bottom right, you see a screenshot of where we're tracking not just the behavior of the players, but also the behavior of the broadcast camera operator. Here, the idea is that we want to model what makes aesthetically pleasing broadcast footage of a game sequence. If you're familiar with photography, there are concepts such as the rule of thirds, framing, and then all those things, and how do we sort of capture that in a dynamic game sequence. In the middle right is a screenshot of a project I did with the Walt Disney Company, where we instrumented an infrared camera in a dark room, and we're watching people watch movies. We're capturing things like their facial expressions, their body postures, and other things like that. And you can imagine correlating these motifs from this type of data to things like the Rotten Tomato ratings. In the middle is a heat map of GPS traces of taxis in Pittsburgh, where I spent 4 years. On the left is a screenshot of 2 fruit flies, or laboratory animals, interacting with each other. At Caltech, we have thousands of hours of fruit flies biting each other. And so if you're interested in that, actually some subset of that is available for download. And so in here, the skeleton is tracked, and so we can actually track the interactions at very fine grain resolution, both temporally and spatially. The bottom left is an application in facial modeling, where we're modeling facial expressions, the mouth, the eyes, etc. The top left is a screenshot from the game World of Warcraft, which is intended to be in a very immersive virtual environment. And so if you have the access to the game engine and all the replay logs, you get perfect tracking completely for free by default. So these are just a few of the many examples and a growing number of examples of ways that we can collect tracking data and of increasing resolution and volume. And from this, we can ask questions of what can we learn from this type of data. And so this is a machine learning talk. I think I will, it's kind of funny. I'll finish the slide. So let me just start by introducing supervised learning, which learns a mapping from some input space to some output space, such that prediction error is low on some training set. Examples include fake news detection, where if X is a body of text and Y was a label fake news, yes or no, we want to learn a predictor that has low prediction error on the training set. So my advisor, Thorsten, made this slide about 15 years ago, and I think it's still somewhat relevant these days. Another example is if X is a DNA sequence and Y was whether or not it encodes some function that you measured from running some experiment, can we predict this well on a training set? And then we could do real value things like measuring the thermal stability, predicting the thermal stability of some protein sequence. You can think of imitation learning, which is the subject of this talk, as a generalization of supervised learning to the sequential decision-making regime. So the input now, rather than in a single X or a single input, is a sequence of inputs, also known as contexts or states, depending on which community you come from. There's some slight differences in what they exactly mean, but those differences are not relevant right now. We often use S to note the input, since it often comes from the reinforcement learning community. And the goal is to predict a sequence of actions, which I denote by A instead of Y. And we learn using sequence of demonstrations. So that's basically what imitation learning is at a 10,000-foot view. Here's one example where we can be a little bit more concrete in the context of sports analytics. So this is a game sequence from a game in the NBA. The red players are the defenders. The green players are on offense, and the orange line is the ball. And let's say we're interested in modeling the green bolded player in question. And so a state is, let's say, the locations of all the players in the ball. We can look at partial information states if you like, but let's keep it simple for now. An action, let's say, is the next location of the player in question at the next time step. We have a training set of such recorded trajectories from the NBA, and the goal is to learn a predictor of this player that mimics or imitates the demonstration as well. So that's what imitation learning is in a nutshell, with a little bit more sort of to a specific example. Okay, so what can we imitate? We can imitate human demonstrations. I'll give you some examples of that. We can imitate animal demonstrations. We can even imitate the demonstrations provided to us by a computational oracle, which can be useful if this computational oracle is expensive or difficult to run at runtime, and we want to imitate its behavior so that we can avoid calling it repeatedly at runtime. Within the context of imitation learning research, we can broadly dichotomize the existing research along two axes. This is, of course, a coarse approximation, but it gets the point across. On the one hand, we have imitation learning from completely pre-collected demonstrations. On the other hand, we have imitation learning where we can have oracle access to a teacher during training, also known as online imitation learning. On the other hand, we have direct policy learning where we try to learn a direct policy mapping from states to actions, typically these days using deep neural nets. On the other hand, we have things like value function learning, also known as inverse reinforcement learning. And within these axes, people have looked at various projects that fill different quadrants of these axes. And from the perspective of the talk that I'll be giving today, at least the previous work that uses deep learning as a policy class, the previous work try as much as possible, to the extent possible, to make minimal assumptions about the phenomenon that they're modeling. This has many benefits. It improves in theory, it increases the generality of their approaches. But for rather complex and structured settings, this can make these approaches somewhat inefficient, in some cases very inefficient. And so my work in this space has largely been working on incorporating various sorts of structure into imitation learning. And you can roughly view that as trying to define a new axis of research questions that's orthogonal to the previous work. Examples that I'll go through today include things like blending black box learning with dynamical systems, or blending black box learning with graphical models. This is a way of incorporating structure in the policy class. Another way is to incorporate structure in the oracle in online imitation learning, where we can design a feedback oracle such that good local feedback ensures good global behavior. Benefits of these types of approaches include things like coming up with systematic ways to introduce better inductive bias into the policy class, where we get faster learning or more sample-efficient learning without compromising on flexibility too much. Most of the approaches are reductions of some sort to conventional learning, and therefore we have oftentimes composable theoretical guarantees. So I will introduce some of the interesting technical questions through the context of 5 applications. So first I'll describe, I'll go through what each of the applications are, then I'll try to motivate and sort of abstract out what are the interesting technical challenges in these applications. So let me start with a fun one, speech animation. And this one's mostly just for fun, but I think you'll like it. So the motivating application is if you talk to an animation artist at Walt Disney Animation or DreamWorks Animation, they'll tell you that especially when animating humanoids, a lot of effort goes into modeling the face, right? You have to get the eyes and the mouth really, really well done. Otherwise, you enter things like the uncanny valley and things don't look good. They oftentimes can look creepy, in fact. And so, mouth movements are, a very high frequency edit, especially if you're synchronizing to spoken audio. And it's very tedious. In fact, the artist often will tell you that it doesn't really leave much room for creative expression. So let's try to automate that away. So data-driven lip syncing. So let me just start with giving you a result that we have. So this is our approach.
Do I look funny to you? I may be a chimp, but I'm dressed better than you.
I'm a PhD specializing in computer graphics and facial animation. But at night, I'm a level 10 operative for a secret organization.
But we are now on different frequencies.
My speech is pretty good, don't you think? Meu português é ainda melhor, não acha?
So let me tell you a little bit about how we set up the problem. So the input is a sequence of phonetics. So this is post-speech processing. You could think of X as a sequence from the IPA, the International Phonetic Alphabet. The output is a sequence of parameterizations of a reference face model. So D is 30 in our experiments. We built a 30-dimensional face model. You could think of this essentially as a virtual puppet. And the goal is to learn to predict the map sequences of X to sequences of Y. And so here's a visualization of such a training set that we've collected. So we had a reference speaker. His name is Ken. That's his face model that we built. He spoke a bunch of sentences for about 8 hours. And the X here is a frame-by-frame decomposition, a phonetic decomposition of the word prediction. The temporal resolution here is 30 hertz, so we're predicting at 30 frames a second. What I'm visualizing down here is the first dimension of a 30-dimensional face model. And dimension 1 corresponds to how wide open the mouth is. So a negative value means the mouth is closed, and a large positive value means the mouth is wide open. And as the Ken starts speaking the word prediction, the mouth sharply opens, stays open for a little bit, half closes, stays half closed for a while, and then completely closes. And that's the type of temporal curvature and dynamics that we like to capture in order to do realistic speech animation. Assuming you've done this well, here's how it would fit into a standard animation production pipeline. You have your input audio. You do off-the-shelf speech recognition, which many companies can provide. We fed the post-process speech recognition into our approach, which does animation of a reference face model. You use standard computer graphics technologies to retarget from our reference face model, which you can think of in this case as an intermediate representation, to any target face model. And this is a one-time operation. It's sometimes expensive, but after you do this, the whole pipeline is automated. And then you can import the high-frequency animations generated by our approach into something like Maya, where an artist can add low-frequency edits, such as smiling. And so that's the entire production pipeline. One nice advantage of this pipeline is that since we're not reliant on audio directly, we can, in theory, do other languages as well. When you saw a sampling of that before, here's a few more examples.
Deutsche Wörter sind sehr viel länger als englische Wörter. Mal sehen, ob das trotzdem funktioniert.
한 가지 언어는 충분하지 못해.
Jeśli kiedykolwiek będziesz odwiedzał Polskę, polecam Kraków.
මම දළදා මාලිගාව වැඳීමට සෙනසුරාදා හවස ගියෙමි.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
That was me speaking Chinese. A lot of fun recording that. We can do singing.
Somewhere over the rainbow, way up high, and the dreams that you've dreamed of once in a lullaby.
Oh, Danny boy, the pipes are calling from glen to glen and down the mountainside.
Okay, so that's all I was going to say about that before I move on to some of the more technical work. But in case there were any questions about that work, I can take a moment for questions. Yes?
Can you go back 2 slides?
2 slides?
Yeah, there. So obviously this is a girl who is singing, but so what does that face mean?
That's the reference face. So our model, and we've tried both decision trees and deep neural nets. It's a sort of a reduction style framework, so you can use any model class you want. That's what we're predicting.
Okay.
Yeah.
And you first predict that face and
That's
then interpret and then transfer that to the animation.
Right. That's right.
Okay.
Yes.
How do you know how well you're doing?
So there's a few different ways. We have a held out set of our reference speaker that we can just test on, and we can look at the reconstruction of the parameterizations of the face, and we can show that we do well. better than baselines. I'm sorry?
You just like measure some standard like
reconstruction error.
With
reconstruction error. The other thing we can do is we can do a side-by-side user study where we say, I'm trying to animate this character with our approach and some standard baseline, and then a user decides which one looks more realistic or more natural or pleasing.
I see. And have you compared yours to the manual artist?
That's interesting. We haven't. Part of that is simply a matter of cost. To get an artist to animate at this temporal resolution is quite expensive. So I don't remember the exact decision making we made at the time. We had a pressure of a SIGGRAPH deadline, but I believe we just decided we just didn't have time to get an artist to animate at that level of temporal resolution. But I suspect that if you actually get an artist to put in the time, they will do better than us. So there is a little bit of a time-effort trade-off here. But our approach runs in real time. Yeah.
How does the generalization work in this? So, like, what is the training set? Do you train over all, like, a lot of...
The training set is 8 hours of input phonetics, strings, and mouth shapes, target mouth shapes.
So you almost read from, like, every possible...
So the 8 hours is from the TIMIT data set, which is a phonetically balanced data set. If you work in speech, language and speech, it's a very popular data set. So it's phonetically balanced. So we have good coverage of all the phonetic transitions that happen in English, which, although we only trained on phonetic transitions that happen in English, it seems to generalize well to other languages, especially those that are closer to English, like German.
More of a philosophical question. Why is this more of an imitation learning as opposed to supervised learning?
In some sense, imitation learning can be viewed as a subset of supervised learning. I mean, it really depends on your perspective. I mean, this is literally behavioral cloning, which is a version of imitation learning. And in fact, people...
So the definition really is a nuance of the definition.
I'm sorry?
I mean, it's literally the nuances on how you... Right. The question really I'm asking is like, when you think about sequence modeling, there's some bit of stochasticity coming from your state transitions, right? And I don't see that here. I mean, it's a deterministic sequence of, where is the stochasticity in the state transition?
So you don't need to have stochasticity. You simply just cannot be able to model the future, right?
So basically, I don't need to know anything about imitation learning if I just use supervised learning.
Yeah, why don't we talk about some of the more sophisticated stuff that we worked on? Like that was just sort of a fun start.
That's fine.
I agree with you.
Nuance just.
I agree with you. It was just behavioral cloning. We're doing sort of sequence modeling. I think one can interpret it as behavioral cloning. I think some of the other work from a technical perspective is more interesting. That was just sort of a fun project that I wanted to show first.
Pretty cool.
Yeah. So let's talk about coordinated learning. So let me start with a motivating application, and then I'll talk about what's interesting about this application from a technical perspective. And so this is an application in sports analytics called ghosting. And what ghosting is you take a replay where the defense performed poorly, and what coaches do traditionally in ghosting is they annotate this replay and superimpose where they thought the defenders should have been to have defended this play better. As you might imagine, this is a very time-consuming effort. And so one thought that we had was, well, why don't we automate this using imitation learning? So one potential application, of course, there are many versions of this, variants of this, is to use, let's say, deep imitation learning to train on the behavior of a better team and then use that to ghost replays of our team as a sort of one example application. And so here, the white is our approach, the blue is on defense, the red is offense. And so what's interesting about this problem is that if you take an off-the-shelf deep imitation learning approach and you apply it directly to this problem, you get results that look like this. Looks like a bunch of 7-year-olds playing soccer. And so what's the issue? And so here's one way to think about what the issue is. For any machine learning approach that's used these days, you require a semantically consistent input representation of the state. In the context of this game, one example of that is you want the first two features of the input to the neural net to be the XY coordinates of the goalkeeper. Then the next two features to be the XY coordinates of the left back, then the left center back, and so on and so forth. That requires knowing who's playing which role. Now, the goalkeeper is pretty easy to figure out, but the other roles are actually not quite easy to figure out. And they're not even annotated in our training set. Our training set is just trajectories. And furthermore, if you talk to a coach, they'll tell you that who plays which role is actually a fluid concept. People swap roles all the time in the course of gameplay. And so this is something that we need to figure out. Because what we have for training data is a set of unordered trajectories. We don't know who belongs to which role. We do have a set of arbitrary player IDs that was sort of given arbitrarily to the data set just to uniquely identify the players. And the original and the baseline that I showed just ignored this basically what's a permutation problem, right? And just sorted the players by the player IDs, and that's how they created the state representation. But to do this quote unquote well, we need to solve this latent variable inference problem where we need to infer who's playing which role. And so what we did was we came up with this framework where we combined imitation learning, any imitation learning you like, with a graphical model approach that inferred the roles as a latent variable in the graphical model, and then used that to sort of create state inputs to the deep imitation learning framework. If you're a Bayesian person or a probabilistic modeling person, you can actually view the whole thing as a giant probabilistic model, where the deep neural nets are basically complex nonlinear transformations of the randomness from the latent variables to the emissions of the output space, which in this case are actions.
When you talk about the roles, do you mean individual players or functions that they're taking on, like forward and defense?
So in this particular approach, we posit that there are different roles, and then we try to group which players are playing which role. At this point, yeah. So the simplest approach actually works quite well, and the simplest approach here is a hidden Markov Gaussian mixture model. So we look at we talk to a sports analyst. They give us a stickiness probability of how likely, if you're playing one role, you're going to keep that role in the next time step, and then there's some prior on the variability of how much variance each role has, and that's the domain knowledge we get from the sports analyst. Put that in here, then we infer the parameters of the Gaussian mixture model in an unsupervised way. Again, if you're a probabilistic modeling or Bayesian person, that you can view the whole training procedure as an instance of variational inference-based learning, and because we do variational inference on this side, and because if you use some sort of policy-based imitation learning approach, the whole thing is a sort of a differentiable learning algorithm.
So neural networks are also Bayesian?
I'm sorry?
The neural networks for the...
No, but they're not explicitly Bayesian. But if you are a probabilistic modeling person, it is valid to view this whole thing as a probabilistic model, where the neural nets are simply a deterministic nonlinear transform from the randomness of the latent variables to the emission probability.
So you're looking at the map estimate and then feeding it?
Correct. Well, during training we sample. At test time we often just take the map. Okay, and so we can visualize the graphical model, and so this was trained on the entire This was trained on the entire English Premier League from the 2012-2013 season. So it's averaged over the defensive play styles of all the teams, but you can see just from this visualization that in the 2012-2013 English Premier League season, the predominant defensive formation is 4-4-2. It just falls out of the data. And we could do things like measure how well we're doing. So here is sort of held out reconstruction error of the positions of the players on held out data. So, and we tried a few different versions of whether or not you do centralized or decentralized policy learning. This is something that has been well studied in multi-agent reinforcement learning. And the thing that's interesting is that whether you try the decentralized or a centralized approach, the difference in performance is dwarfed by whether or not you incorporate this graphical model. And that was the point we're trying to make in this slide. Yes?
What if I do something much more naive, where I don't try to get the roles? I just let's say have two image frames, one annotated with white for where all the locations of team A is, and B for the team B, and then just feed them in as to a CNN, and because the output is what should, like, let's say the player one should, all the players should do, right, as actions, and you're feeding and learning from temporal sequences.
What should all the players do? So what is the output space?
So the output space is, let's say, 12-dimensional, and it gives you the velocities of
every player
for the next frame, what they should do, given that. And you can have a sequence.
And how do you decide which player belongs to which output dimension?
That you just fix, right?
Okay, I don't know the answer, but I suspect you get similar issues because.
But yeah, you can do dagger or aggravate and whatnot.
So here, each player you just fix an output dimension, and you get. I mean, we're not using CNN, but in terms of the output space, we're doing exactly as you suggested, where each player is just arbitrarily fixed to one of the output dimensions.
Okay.
Like, there's hundreds of players in the English Premier League. They're not playing all the time. They swap roles all the time.
No,
so,
I'm just saying, like, do away with identity and.
Yeah, so that's essentially what we're doing here.
I see.
Not the input space, but the output space.
But output space.
Yeah.
Some other feature hypothesis.
Yeah.
Okay.
The way we predict the outputs is exactly as you described.
And that doesn't learn even if you use, like, dagger or whatnot.
This is using dagger. This is dagger.
Interesting.
Yeah.
We'll have it offline.
Yeah.
I'm really interested.
Yeah. I think it was dagger. It was either dagger or CERN. It wasn't very that difference wasn't very meaningful compared to yeah. Okay, let me move on to talk about hierarchical behaviors. So now, before I was talking about defense, now I'm going to shift and focus on trying to model the offense. And when we make decisions in life over a long time sequences, we often make decisions that are in some sense hierarchical in nature. There are long-term goals and short-term goals, right? And so in the context of this sports example, we can have a long-term goal, like the player in question wants to pass the ball and curl around the basket. And the short-term goal, or the tactics, if you will, is the step-by-step sequence of actions that this player takes to achieve that long-term goal. And so focusing on offense, thinking about how to model offense, which is typically has more of a planning flavor and is less reactive than defense. We started thinking about two things. One is generative imitation learning. One is hierarchical imitation learning. The reason we're doing generative imitation learning is because you actually want to be a bit unpredictable in offense. The behavior is actually quite multimodal. If you're predictable, you're easier to defend. And hierarchical so that we can capture the making predictions or planning at multiple resolutions. So one idea that we've been looking at is using weak labels generated that can annotate some sort of intermediate goal. And this is what we call macro goals. So this player first wants to reach this location. That's a macro goal. And after this player reaches this location, the player changes macro goals. And that gets fed into a hierarchical deep generative model. The specific model is not important. We use a variational recurrent neural net. And what happens is we sample a coordinated set of macro goals for all 5 players on offense, and then condition on the 5 macro goals, the individual actions of each agent is sampled independently. And so we could do rollouts from this approach. So this is a comparison of our approach on the left versus a standard baseline on the right that doesn't use macro goals. Now, you may not follow basketball very closely, but just believe when I tell you that green player in the middle should not have run off the court. We can also sample not just the low-level behavior, we'll sample the macro goals. So here we're showing a visualization where we're sampling the macro goals in time as well.
Is there any representation of the defense in this?
Here we're just, you can think of this.
That's clearly going to affect your goal.
It is. I think we ignore the defense for a couple of reasons. You can interpret this as just sort of averaging out what the defense should have done. So in practice, when people practice offensive set sequences, the defense isn't really there. They just sort of execute the different plays. And so we're just trying to sort of average over all the play sequences, trying to recover that distribution. Conditioning on the defense is, of course, also important next step. You can sample repeatedly from the same initial conditions, and you can see that we do learn interesting multimodal distributions of trajectories. And interestingly, if you ground the macro goals are interpretable in a very concrete sense. And if you ground them, the low-level trajectories are sampled in a way that adheres to the macro goals. We can do a similar type of work in the context of modeling animal behaviors. So here is it playing? Oh my, something crashed. No. So we do something similar with animal behavior. So here's a petri dish of fruit flies interacting with each other. One of these is actually real video. One of these is synthesized. Not sure if anyone here can tell the difference. A biologist can tell the difference immediately. The one on your left is real, and the one on the right is synthesized. The one on the left has a behavior of males chasing females. And we sort of forgot to use gender as an feature attribute to our model, so all of our fruit flies are androgynous, so we weren't able to pick up on that statistic. Of course, this is something we can add later. But with fruit flies, you have similar kinds of high-level and low-level actions. So for example, if one fruit fly decides to charge another fruit fly, that leads to a sequence of actions, time frame by time frame, that executes a charge action. So we can sort of do similar types of analysis in fruit flies. If you're interested in details, I was in an iClear paper last year. And just as an aside, this is a project we did. My student did while he was an intern. Primarily did while he was an intern at Microsoft, Huang. You can think about hierarchical modeling that blends between imitation learning and reinforcement learning. One of the issues with imitation learning is that in many applications, one concern is how the cost of collecting demonstrations. On the flip side, in reinforcement learning, if you're in a sparse reward environment, such as Montezuma's Revenge, the cost of exploration can be challenging. And so hierarchical policy classes provide a natural framework to blend imitation learning and reinforcement learning, where the top-level hierarchy is trained using imitation learning. And in this case, concretely, a human would say, first go here, then go get the key, then go here, and then go out the door. Where the sparse rewards from the game environment would only give you a reward if you get the key and go out the door. And then the low-level planners are trained using standard reinforcement learning. And with a very modest amount of demonstration data at the high level, we trained a hierarchical approach that was much more efficient than standard hierarchical reinforcement learning. So that's a hierarchical DQN that we compared with. That's the green line. It basically gets 0 reward up to 4 million samples. And these are different versions of our approach. Yes?
So for the high-level goals, you mentioned with little or small amount of supervised signal. So how do you, could you share more details about
in this particular case, we literally just clicked on this. I mean, there's a few different ways to do this. One way is to simply click on the screen and then do pattern matching whether Pedro, the main character in Montezuma's Revenge, reached that location.
So it's human annotated.
This is imitation learning, yeah. So there's labeling or demonstrations involved.
So have you ever tried just to learn the high-level goals by itself?
That's essentially what hierarchical reinforcement learning does. And I mean, thus far, the evidence suggests that it's very inefficient from a sample complexity point of view. Okay, let me move on to learning to optimize. So here we're going to look at various forms of optimization problems, and we're going to view them from the context of sequential decision making. So many solvers are sequential in nature. The greedy algorithm is sequential. Various search heuristics like tree search, branch and bound, are sequential. Gradient descent is a sequential solver. And so we could view these solvers as quote-unquote agents, where a state that we input to the agent is some representation of the optimization problem and the intermediate solution. And the goal is to find a state with high reward. For example, if we're trying to solve an integer program through some sort of tree search algorithm, such as branch and bound, we want to find a feasible solution. That's the only place in an integer program where we do have reward. And so in this context, my group and our collaborators have looked at a few different problems. One is learning to, and Day was a co-author on this paper, learning to mimic a greedy algorithm for some modular optimization, where we want to train a policy that mimics the decision-making of the greedy algorithm without having to query the modular function, which may be expensive to query because it requires calling a simulator. It may even be difficult to query at test time if you haven't sensed the environment properly. We've looked at learning to search in branch and bound for integer programs. So if the input environment is an integer program and it's tree search representation, and we suppose we had a demonstration of a solution given to us by Cplex or Gurubi or some other commercial solver, can we train a neural net to navigate this space more efficiently than the initial demonstrations? We've also done work in continuous optimization problems rather than discrete optimization problems. So specifically, in the context of learning to infer, many of the most popular inference approaches in probabilistic modeling these days are based on variational inference, which converts the inference problem into an optimization problem. And so you're basically navigating in typically a non-convex optimization landscape to do inference. And if you want to do this quickly, maybe you want to use a neural net to sort of navigate that landscape quickly. If you're familiar with variational autoencoders learns a single neural net learns a neural net that does a single mapping of the inference problem that tries to predict the optimal solution of the variational inference problem in one shot. And you could think of this as a sequential generalization of variational autoencoders that does iterative applications of optimization using a neural net that learns to amortize the inference. For the interest of time, I'm just going to talk to you some details of the middle project on learning to search. And so this project was originally motivated with a collaboration with JPL and NASA on risk-aware planning. So imagine you're the Mars rover, and you're planning a trajectory on a potentially hazardous terrain or domain, such as Mars, and you have very strict bounds on risk tolerance. And so what used to be a fairly straightforward dynamic programming or Dijkstra's algorithm type problem now becomes NP hard because of all of these hard constraints. And this is typically compiled as an integer program. And so here's how we set up the problem. Suppose we had a distribution of planning problems from which we can draw training examples. Examples include terrains from Mars. That gets compiled into some kind of combinatorial search problem. In this case, it's an integer program. But really what we care about is the fact that we have a combinatorial search tree structure as the environment. We have some initial demonstrations. In this case, the expert demonstrations come from Gurubi or Cplex or some off-the-shelf integer program solver, which does find a feasible solution, but perhaps makes many mistakes. We do imitation learning on these demonstrations to learn a neural net that can act as the search heuristic within a tree search procedure. And then we apply it to test instances drawn from the same distribution as the training instances.
Part is basically solving this integer program.
That's right. Yeah, so here's the imitation learning approach that we proposed for this setting. It's called retrospective imitation. So we start with an expert trace that finds a feasible solution, but perhaps makes mistakes. Now, if an expert makes no mistakes, you can solve an integer program in linear time. Just set each integer variable one at a time. Linear in the number of integer variables. If an expert is really, really bad, it takes exponential time, basically, to solve the search trace, solve this integer program, and the search trace would then be exponentially large. Most commercial solvers do a somewhat reasonable job and do manage to find feasible solutions, at least on smaller problems, although not in completely linear time, so there are mistakes. So the idea then is to use imitation learning, and our approach is composable again with many different imitation learning approaches. I'm here using Dagger for just concreteness. And we basically, at each point in the search tree, there's a correct decision and there's an incorrect decision, assuming you know where a single feasible solution is. And that's the imitation learning reduction. We roll out our policy on the environment, and perhaps we make more mistakes. Perhaps we can find a integer solution better, that's better in some sense. We use what's called this is sort of our core innovation. We introduce what's called a retrospective oracle that takes a look at the environmental rewards. So the environmental rewards here comes from the description of the mathematical optimization problem. Did you find a feasible solution, yes or no, in the simplest case? And that's a sparse environmental reward. You could, in theory, directly use that for reinforcement learning, but it's very hard because of the sparseness of the rewards. But through the retrospective oracle, we can convert this back into an imitation learning problem where we can take a look at this trace and figure out at each state in the search trace that we visited, what is the correct decision. In this case, it's branching left or right, although in general, the branching factor is quite large. We then repeat this process until we've converged. And this is what we call retrospective imitation learning. It basically takes sparse environmental rewards of a certain flavor and interfaces that back with imitation learning. Yeah?
The earlier levels of the search tree, it looks like I basically get no learning signal, right? It's like that exists a feasible solution in each of the subtrees.
It's not necessarily true because the branching factor is huge. Like there might be, if there's 500 integer variables, the branching factor is essentially 500, right? And maybe 2 or 3 of them might lead to good feasible solutions, and the rest they don't. So it seems true here simply because of the toyness of the visualization example. Okay, and so here's some results that we have. So this is optimality gap. So in these examples, we basically ran the solution. We ran a solver exhaustively until we eventually found the optimal solution. So we could. I'm really glad that was recorded for posterity. So anyways, so here in these examples we managed to run the solvers exhaustively, so we know what the optimal solution is. So lower is better. We're measuring the optimality gap, and so you see a comparison between Gurubi, which is a commercial solver, an open source solver, and our approach. And this result actually I find quite surprising. And by the way, the x-axis is the size of the integer program, from 400 integer variables to 560 integer variables for the planning problem of different levels of complexity. I actually find the result kind of surprising. I wasn't expecting us to do this well. Furthermore, our approach learned only from Gurubi demonstrations at size 400 integer variables. And for all subsequent problem sizes, we actually bootstrap from our own policy as the initial demonstrator. And so in theory, if Gurubi was too expensive to run at 500 integer variables, it's totally fine. We can train our approach from demonstrations at 400 variables and then bootstrap itself and scale up to more complex problems. Yes?
I think I'm missing something pretty basic here. So I don't really understand why you need any demonstrations at all. Why isn't this a pure explore exploit? Like, if you can bootstrap, why not start from nothing?
Well, the reason, I have another curve where we show reinforcement learning. It's way up there. The reason is the cost of exploration. So if the reward is sparse, right, and you need to make 500 decisions before you see a reward 0 or 1, then, I mean, in the worst case, that is exponential in 500.
Just because you know when you've solved it. What if this were like a architecture search in neural network, like in auto ML kind of thing? So there's no one solution you need to find, but you just need to do well. Would that make it dense enough to not require
possibly. You'd have to look at it on a case-by-case basis. I think it's possible that in that case it's dense enough where you don't need to do this. But for solving hard combinatorial optimization problems where the reward is literally, you only get a reward at the end, did you find a good feasible solution, yes or no? The cost of exploration is, I mean, I don't have a proof, but intuitively it's exponential.
So these safety constraints are coming from STL or something like formal?
Yeah, they come from various constraints. Sometimes from temporal logic. Yes, that's right.
How do you now preserve the optimality guarantees, like safety guarantees? Because if I were to solve those programs, I know that I'm never violating those constraints. Now you replace that thing with a black box, and there's no guarantee that the safety will be ensured.
The guarantee is ensured by the description of the mathematical program. We're not actually using the black box to make decisions directly. We're using
Aren't you proposing that you will be using that neural network that's trained, using the data that you generated to now?
Yeah, but this I'm simply choosing how to set the integer variables of a mathematical optimization problem. If I find a feasible solution, it satisfies all the constraints. It satisfies.
No, that's fine, but then you're training your policy with it, right? It's the policy that you're going to run.
The policy is simply navigating the combinatorial search space of the planning problem. It's not actually directly making any decisions.
So I think probably we'll take it offline. So I'm very interested in figuring out like how do you ensure safety constraints at the runtime?
So in this case, suppose you had an I've actually spent a lot of time thinking about this as well. In this case, suppose that we had a reasonable description of the environment, and we have ways of ensuring safety. The hard part, which is not always true, but suppose that were true, the hard part then is the combinatorial problem of finding a plan that satisfies safety. And if you could find such a plan that satisfies those constraints, which you can describe up front with perfect sensing and all that, then you're done. And so we're basically just navigating that combinatorial search space with a neural net. And if you find a state that satisfies all the constraints, you're done. You're provably safe.
I see. So it's basically just letting you search through that.
That's right.
Okay.
Yeah.
So policy in the runtime.
That's right. Yeah. We're basically trying to find a safe plan at runtime as quickly as possible, and the safety is guaranteed by the constraints of the mathematical program, which assumes that you've already done sufficiently perfect sensing and all that stuff. So we're abstracting that away. So this is really focused on combinatorial search problems with certain hard constraints. Yeah. Okay, so I'm going to move on to the last topic, which hopefully I'll finish in about 5 minutes, on smooth imitation learning. So let me again first describe the motivating applications. This is a project in collaboration with Disney Research and ESPN. So here we have real-time player tracking, and because it's real-time and not processed offline and cleaned offline, the tracking can be quite noisy. We have a human camera operator that is composing game footage that's aesthetically pleasing to track the action, and the goal is to train an autonomous camera policy that can imitate the behavior of the professional expert. So here's the problem formulation. We have a stream of exogenous context, which is what the players are doing on the court, and their detections are noisy. A state is a tuple of recent locations of the players and recent configurations of the camera. So this is where we're pointing the camera, the internal state of the camera. And the goal is to learn a mapping from states to actions that imitates the expert. So my collaborators, who are roboticists, the first thing you would think of is to try a purely supervised learning approach in terms of conventional supervised learning, which is to train a predictor per frame and then make predictions per frame and then stitch the predictions together. And you get a result that looks like this. So the y-axis is the pan angle of the camera. The black is the ground truth expert for this particular game sequence. And the red is the predictions of a standard supervised learner. And it's pretty accurate on average. The problem is that it's extremely jittery. You would not actually want to watch game footage composed by the red line. You'd probably get a headache, potentially even throw up. And the problem essentially is that we've taken what was a sequential prediction problem with some, at least intuitively, some constraints on the sequential dynamics, such as smoothness, and we've basically thrown that away and turned it into an IAD supervised learning problem where we predict each frame independently. And so if you wanted to train a concept like temporal smoothness using only input-output examples, which is what modern machine learning is reliant on, then for every possible sequence you want that the predictor could possibly predict, you want to teach it to make a smooth correction. And I'm only being sort of semi-facetious here when I say that if you want to do that using only input-output examples, it quote-unquote takes an infinite amount of training data for a continuous output space. In practice, most people do post hoc smoothing. So, for example, people have model-based smoothing based on things like Kalman filters, based on parametric autoregressors like linear autoregressors, and they apply that to the trajectory of the camera behavior and they smooth it out. The problem is that these model-based approaches have a hard time modeling arbitrary features such as noisy player detections, and so they typically just ignore those and just smooth just on the trajectory of the camera. And so you're ignorant of the game context, so you tend to over-smooth or under-smooth at different places. And so we looked at this problem for a while, and one lesson that I took away from it was that for these type of applications, you really don't want to rely 100% on black box learning. People, from aerospace, from various control communities, have many different models of smoothness and other notions of stability. Kalman filters, linear autoregressors, just a few of the basic examples. You can analyze the spectrum of the transition matrix of the Kalman filter to look at its stability properties. You can easily regularize a linear autoregressor to be provably smooth. And a pure black box learning approach throws all of that away. It tries to learn everything using only input-output examples. And so we've been looking out how to build these hybrid approaches that has some dynamics, model-based dynamics built in, and combine it with black box. So you inherit both the structure of the model-based approaches and the flexibility of black box approaches. And so this is the policy class that we introduced to get at this, and it works pretty well for our application. And I'll describe it. So the policy predicts a blending of a black box predictor and a smooth model. So the black box predictor is denoted by F, and the smooth model is denoted by G. This particular policy predicts a compromise between the two. And since the compromise in the simplest case is measured using squared error, or squared deviation, it has a closed form formula. And what we're basically doing is we are making a prediction with the smooth model, and then predicting a residual course correction, if you will, with the neural net, with lambda controlling the trade-off. In our experiments, lambda is 10. It's an easy parameter to tune. And so in some sense, we only need to model what the model-based, we don't need the neural net to learn to predict what the model-based approach gets wrong, the residual, if you will. Another way to think about this situation is that, well, okay, suppose G was a linear autoregressor. G is actually a very simple neural net. A linear autoregressor is a very simple neural net, actually. And so G is actually a subset of F. And what that means is that H is a subclass of F. Our class of policies is a constrained class of neural nets. And the constraint comes from wanting to make predictions, sequences of predictions that are close to the sequence of predictions from some smooth model. So you could think of this as a form of regularization. But we're not regularizing parameter space, which is hard to do for neural nets anyways to get what you want. We're regularizing the sequential behavior space of the neural net. Furthermore, this is a form of regularization that is not just used at training time, in which case it's hard to actually leverage this kind of regularization because you have to enumerate overall possible state action outputs to do this kind of regularization at training time. This is a regularization that you take with you at runtime. If you can prove properties about G, such as something about its stability, for sufficiently large lambda and F that's bounded in some way, H, you can assert a similar stability property on H. And you don't need to sort of exhaustively enumerate overall states to do that. You can just simply, if you can assert it on G, you can assert it on H for some properties. And so this actually gives us an advantage in terms of not having to enumerate overall possible states to actually ensure this kind of stability property because it's with you at runtime. Yes?
I think this G, will it make F smoother, or in practice it doesn't? F is still very jittery.
Yeah, so let's look at our results. So here's our results. So the blue is ground truth and red is our approach. So we're both accurate and smooth with only 30 minutes of demonstration data from the expert.
How about F itself?
Actually, it's a good question. Well, it's hard to visualize F itself because F is predicting the residual of G. So the prediction of F itself is somewhat meaningless. Well, unless you look at we can take that offline. I'm not sure how to answer your question. We didn't look at F directly by itself. Because the way we think about it, or the way I think about it, is that H is a neural net, right? This is a simple neural net. This is a full-fledged neural net. Its blending is still a neural net. And this is the behavior of that blending.
Do you have a visualization for different choices of lambda, and how does this behave?
I do, but in the paper, not on the slides.
You mentioned it's easy to tune. How do you tune it?
We tried 10 different values of lambda, and so here's one way to do it. You can do so you could choose. Let me comment on that a little bit more specifically. You can choose lambda in a way such that you can certify certain guarantees on H. If lambda is not big enough, you can't certify anything. You can choose lambda. So the learning basically says I want to train the most accurate model possible, subject to the smoothest constraint. And it's a single tuning parameter. So it's one-dimensional tuning parameters are easy to tune, especially one with these kind of semantics. And so you can tune it and then look at the output and decide if you could decide with a roboticist whether or not this is an appropriate level of smoothness. And that's what I mean by easier to tune. A formal theory of how to select lambda in a more meta approach we don't have.
FNG are separate architectures.
I'm sorry?
FNGs are separate neural networks that you're training.
Well, G is a linear autoregressor. It's a kind of a super simple neural net. But yeah.
Basically, it's a neural network, the whole thing, but you have decomposed into actions.
That's right. You can interpret the whole thing as a giant neural net that's constrained, but in practice, we decompose it. So here's just I'm running short on time, so apologies. Here's just a visualization. So we superimposed the predictions onto the original game footage, and we compared our approach versus a standard two-step baseline. So you can get the game footage on your right automatically with our approach now. And funnily enough, I believe this was the first time that a machine learning paper was covered on Sports Illustrated. Okay, I'm running short on time, so I'm going to skip some of the details of the learning algorithm.
We have 10 more minutes.
Oh, okay. Okay, so I wanted to take a little bit of time to talk about some of the technical details, since most of the previous examples I sort of skipped over some of the low-level technical details. And so, first the definition of rollout. So a rollout roughly means we're going to execute our policy sequentially, and then we're going to collect some kind of relevant statistics to use for learning. Common things to collect are things like state-reward pairs for reinforcement learning, or just simply state distributions for us. So here's two rollouts of the smooth imitation learning policy at different iterations of learning. So this is the rollout, and this is the second rollout. We could collect something about statistics about these rollouts and compare them to the ground truth for learning. And so the way we do learning is through what's called a learning reduction. This was pioneered by John Langford and his collaborators. And so here's the idea. We have an original learning problem in sequential decision making. We want to convert it to a learning problem that's easier to solve, typically just standard one-shot classification or one-shot regression. We run training on this simpler problem using standard off-the-shelf machine learning toolkits that have already been extensively debugged and engineered for performance. So we train H on D prime, easy to do. And then our theoretical goals are then when we apply H to the original problem D, that whatever guarantees we get on D prime lift to D, and of course that it works well in practice. And so this is our learning algorithm. It's called Simile. It's an extension of an imitation learning algorithm, CERN, which was proposed by Hal Domey, John Langford, and Daniel Marcu. So we have an initial predictor where we memorize the demonstrations, that's H naught. And for each iteration of learning, so we generate a sequence of these learning reductions to supervised learning. For each iteration of learning denoted by a little script M, we roll out H on the game context. We obtain a training data for supervised training data D prime. We train a new policy, and then we blend this policy with the previous policies to obtain our overall policy. So this is at this level of detail, this is a fairly standard imitation learning algorithm. The two key things that we need to instantiate for our approach is this guy, how do we collect feedback to create D prime, and how do we actually train H with this blended model class. For smooth feedback, we create feedback of the following form. Suppose we train a policy that wasn't very accurate yet, and during rollout, it's quite far from the optimal camera behavior. Then the ground truth, the regression target when we create D prime, typically in standard imitation learning, you'd want it to go all the way back to the ground to the camera's operator's ground truth. But because we want to ensure smoothness at every round of learning, we create a smooth feedback, and how exactly you choose this is described in technical detail in our paper. But that's the intuition. And so with that, we get this theoretical guarantee where we're always smooth, right? With the smooth feedback, we're always smooth. We have guaranteed improvement, so we leverage the conservative policy improvement lemma from Kakade and Langford. So we guarantee to converge to an optimal, near optimal smooth model, subject to the supervised learning guarantees that we reduce to. And the key thing that we innovate on in terms of the low-level technical details is an adaptive learning rate beta. So typically in CERN, which was proposed before, they use a fixed learning rate, which leads to actually very slow convergence in theory. And we could provably use an adaptive learning rate that exploits the Lipschitz property of the policy class that's induced by having a smooth model. And what this means is that we converge much, much, much faster than CERN. And this is analogous to if you think about gradient descent, you use some small fixed step size, or you can use an adaptive step size if you think you can make a big progress in that direction. In CERN, they use just a small fixed step size, and you just, in practice, what they do is you just set beta to be a really small number, and then you just see how well it converges. With our approach, you can set an adaptive beta. So this is the beta that's theoretically justified by our theorem, and it converges much faster. Yes?
Could you get the smoothness not by this, but by just changing your state representation? So if I take in the previous state and the current state as my state input.
So we do that. We actually look at a recent history.
Uh-huh.
And well, at least just straight up applying a neural net to that doesn't work.
It's still noisy.
No. Yeah, that's right. Okay, so what are some lessons learned? If we have a model that characterizes a lot of the desired behavior of the phenomenon that we're trying to capture, let that model do as much of the work as possible. Right? And we simply use deep learning or black box function fitting to add a layer of flexibility on top of that model. In some cases, such as the project I just presented to you, you can actually interpret this blending as a form of regularization on the deep neural net, which then you can use to improve or speed up learning. And in fact, we show exponentially faster convergence compared to CERN. And this exploits the Lipschitz property of the smooth temporal dynamics that we're able to provably certify in our policy class. And one question is, can we apply this to other approaches? And this talk that I'm giving today is actually a little dated. We have some very new recent results at the combination of deep learning with model-based robust control. This is work with Aaron Ames and Soonjun Chung, who are two robotics professors at Caltech. And I'll be excited to talk about that offline. And so just to summarize, I've shown you 5 applications of imitation learning. Speech animation, coordinated learning, hierarchical behaviors, learning to optimize, and smooth imitation learning. And I hope I've convinced you that there's some really interesting new frontiers in research in imitation learning. In particular, I've shown you some interesting questions about how do we incorporate structure to better regularize or improve the inductive bias of the learning problem. In particular, how do we model smoothness of the output space, the latent permutation structure of the input space, new feedback oracles that convert hard sequential tissue-making problems to good local feedback. And we've introduced new algorithmic frameworks that blend black box learning with model-based dynamics, or black box learning with latent graphical models, or retrospective imitation learning oracles. And of course, many cool new applications that have already been made possible with these approaches. Many of these are used in production already. Finally, I'd like to thank all my collaborators, especially the students and postdocs in the top row who did most of the actual work, and I'm just standing here getting to talk about it and looking pretty. And if you're interested in any of the technical details, most of the work that I presented to you are available on my website. Thank you for your attention.
Take some questions.
Yes.
On the new algorithm, the one in the last section. So would you? So I'm trying to understand the smoothness guarantee, because the algorithmic framework is very standard.
That's right.
Like, and it seems like that. Is it? Would you say that it's like just for me to place in my head? It's like if I were to do aggravate, but get instead of rolling out for many steps, I cut it off and say that you only roll out for a little bit, because I can still show convergence in that respect. It would give me smoothness, and how you cut it off matters.
I think so. First of all, you can do aggravate. You can do aggravate with this policy class, and I tend to. So to a first order approximation, I tend to think of things like aggravate as trying to solve a complementary problem than what this is trying to solve, in the following sense. How do you certify the behavior of your black box policy class to be regularized to have certain behavior? If you only certify it through rollouts, then in the worst case, it takes exponential time to certify that behavior. If I blend my black box policy class with a model-based policy class that I can provably certify analytically, then in some cases I can certify the whole policy class.
I see.
Yeah.
So that's why you are using like a CPI-like update, like a natural policy gradient update.
That's right.
To ensure smoothness in subsequent distributions.
That's right. Yeah. So I think you can actually you can blend you can do this on top of Dagger or Aggravate or anything. I think it. I'm sorry.
So that's independent.
I think it's orthogonal. Like
yeah.
Okay. I think it's really how do you certify that your neural net or black box function class, I don't want to be beholden to neural nets, maybe, but your black box function class satisfies certain certifiable properties, and then subsequently, can you exploit that to accelerate learning? Those are two separate questions in my view, because you could also use the smooth policy class for reinforcement learning, but the learning algorithm will be a little bit different, right? Because it has to do some amount of exploration. So those are two separate questions, and although this is an imitation learning talk, I'm more excited about the definition of this policy class than I am about the imitation learning algorithm that was derived from it. Yeah.
Cool. Yeah. One high-level question I had, that you're mixing, these black box learning methods with techniques from Bayesian inference.
Sometimes, yes. Mm-hmm.
Yeah, right. So, any thoughts on trade-off between, fully Bayesian neural networks versus what are the trade-offs have you seen in your work?
Fully Bayesian neural networks.
Otherwise, then I can run the inference end to end, as opposed to playing this trick between map or sampling and then optimizing and all that.
I see.
Have you thought about even doing so?
Right. I have briefly. We haven't really done that research on fully Bayesian neural nets for imitation learning in great detail. The reason was one of practical expediency. We wanted to build frameworks that were built on top of classical imitation learning approaches, and so from that perspective, that's the perspective that we were looking at. If you were going to try to do fully Bayesian deep learning-based imitation learning, it would require a more dramatic departure from classical imitation learning in a way that would require, substantially more engineering work potentially.
Alternatively,
yeah.
You consider the hidden variables in probabilistic world, and your parameters of your neural network, the things that you optimize over. Right now, there's a disjoint in training and inference, but you could actually frame it as in a single framework where you do inference over the latent variable, and then very, very similar to variational, but you still keep the computational advantages of, I guess, model fitting, but still the flexibility of Bayesian graphical model. You can take this thing offline, but what I'm saying is that instead of piecewise optimization and inference, you can jointly do that.
In some sense, we are jointly doing it end to end. The gradient of the variation inference of the graphical model, can take gradients from the imitation learning, especially if you're using something like. So if you use something like Aggravated for the imitation learning framework, which is a differentiable imitation learning algorithm, you can actually train the whole thing end to end. We didn't do that for this particular paper, but in terms of getting the math and the gradients to line up together, that's not a problem.
But computation-wise, does it make sense?
Computation-wise, potentially. We just used. Because we were focused on just how to even set up the problem. We mostly resorted to either Dagger or CERN just to keep things grounded. But I haven't done the numerical experiments. But my suspicion is that if you blend this with Aggravate and you do fully end-to-end differentiable variational deep imitation learning, it will be faster. But we didn't run the experiment. Yes.
Many of the ideas you suggested, like incorporating structure into the policy class, also apply to sequential prediction problems, right? If I'm just viewing this not as actual interventions and predicting actions, if you hadn't shown me all the speech animation or all these things where you actually let the policy now intervene in the real world, and you only showed me reconstruction errors.
Sure, sequential prediction is a special case of imitation learning.
Right.
Sure, yes.
So I'm curious, to what extent do you see all these benefits were coming from just better sequential prediction models versus a better interface between that and the imitation learning algorithms like Dagger or CERN or things like that?
Right. So in some sense, the core imitation learning algorithms that I'm describing are basically the same algorithms that people have been using for the last 15 years. So in some sense, we're not really innovating in that space. We're really innovating how do we compose new function classes, if you will, with core imitation learning algorithms to create these more holistic frameworks that go far beyond, in terms of practical applications, what core imitation learning algorithms can do by themselves with just standard function classes. But yeah, I don't think we've proposed any imitation learning algorithm, core imitation learning algorithm that's substantially different from any that we've seen in the last 10 to 15 years.
But do you see opportunity to now incorporate new structures?
Well, I've come to really admire the learning reductions approach that John Lankford has pioneered in the last few years, and so I'm not so interested in that actually. I really, the marginal gain of getting a slightly better core imitation learning algorithm, in my opinion, at least in collaborations I've worked at, is dwarfed by the potential to just do something, how to model the layer of abstraction on top of it. And so, for me, the answer is no. All right, thank you.